Okay, so let me start by convincing you why we can use matrix completion algorithm like collaborative filtering. Note that after the transformation we did with our data, we have a matrix with known entries being +1 or -1. The unknown entries that we want to predict is really matrix completion problem for that reason. Let us recall one such algorithm, user-user collaborative filtering. Suppose you and I are two users. We have provided preferences for a collection of movies. Some movies for which you have provided preference but I have not. Some movies for which I have provided preference but you have not. And some movies over which you and I share preferences. Let us suppose there are 3 movies for which both you and I have provided preferences. Let us say those 3 movies are A, B and C. The corresponding pairs would be A compared with B, B compared with C and C compared with A. These correspond to 3 different columns in our matrix. For each of these columns, we have provided values of +1 or -1. I like A over B, I like B over C and I like A over C. On the other hand, you might have liked A over B, C over B and A over C. Looking at the overlap of these 3 columns, it seems that you and I agree on 2 out of these 3 entries. After computing similarity using cosine of our vectors restricted to the overlap of these 3 columns, we get similarity of 1 over 3. Now suppose you have provided ranking of Iron Man preferred over Superman, but my ranking for Iron Man versus Superman is unknown. Then we can use similarity between you and me to transport your +1, that is you liking Iron Man over Superman, to my setting with the similarity weight of 1/3 that we just computed. Now suppose in addition there is our common friend, say Philip, who has also provided preferences over A, B and C. Then his similarity to myself is -1 over 3. And now suppose Philip does not like Iron Man over Superman, that is, he has given preference for Iron Man compared to Superman as -1, then we can use his -1 with weight of -1 over 3. Putting all of these things together, we obtain prediction as follows: 1 over 3 for similarity between you and me, multiplied by +1 coming from you, plus -1 over 3 for similarity between Philip and me, times -1 coming from Philip's preferences. This whole thing divided by 2/3 comes out to be 1. That is, our prediction is +1. Ah, that's nice. Effectively, you are like me and you like Iron Man. On the other hand, Philip is not like me and he did not like Iron Man. And hence, when we combine both of these weighted preferences together, they end up suggesting that Iron Man is preferred over Superman, that is +1. But now suppose Philip actually had liked Iron Man and Philip's similarity to me was -1 rather than -1 over 3. Then the prediction would be, just quickly recalling the same calculation with different numbers, is 1 over 3 times +1 plus -1 times +1, and this whole thing divided by 4/3. This, after a simple calculation, will turn out to be -half. This example provides intuition why we will see predicted values that are not necessarily +1 and -1, but values most likely in between. This example also explains how collaborative filtering like matrix completion algorithm can be directly used in our setting. Now we will address the second challenge of obtaining ranking for movies using these predicted scores for movie pairs. Let us look at any 2 movie pairs, say Iron Man and Superman as before. The score of -half between them suggests that Superman is preferred over Iron Man. One way to interpret this is in the form of random outcome of games. To understand what -half means, let us consider special values of -1, 0 and +1 first. -1 means that Iron Man always loses compared to Superman. +1 means Iron Man always wins, and 0 means that Iron Man wins half of the time, Superman wins half of the time. This suggests that if predicted number between -1 and 1 is, say, x, then it can be thought of as tossing a coin with bias p, where p is equal to 1 plus that x whole thing divided by 2. When outcome of coin toss is head, which happens with probability p, Iron Man wins. When outcome is tail, Iron Man loses. Therefore, we can convert each of the predicted value for a given user row by adding +1 to it and then dividing the resulting value by 2. This gives us probability of one of the movie winning against the other movie amongst the pair of the movies that the column corresponds to. If it was -half, then p equals to 1/4. That is, Iron Man wins only 25% of the time against Superman. Now we are back to the setting where we have a collection of movies, and between pair of these movies, we know what fraction of time one movie wins over another movie. This is exactly the setting for which rank centrality was designed to obtain global ranking. That means that we can now apply rank centrality over all movies and obtain a global ranking among them for each user separately. And this gives us personalized ranking for movies. In summary, we discussed how to obtain personalized ranking when preference data is available in form of comparisons rather than ratings. There is nothing new about the algorithm. It is about putting two algorithms that we have learned earlier: matrix completion algorithm like collaborative filtering and rank centrality for obtaining global ranking between objects using pairwise comparison data. Next, we shall discuss other approaches for personalization beyond what we have already discussed. Thank you.